bring a wireless mouse so you can forward it?
No, but I can poke the keyboard with a stick.
I have a wireless mouse.
Alright, my name is David Riemann, and I will be sharing the pink team's results for the steady state operating curve and the step response results for the spray paint pressure booth. Today I'll be going over the systems information, the steady state operating curve results, the step response results, and the conclusions that we got from running these experiments. Some background information about this system. This system is based off of a spray paint system that is used to paint engine housings in Dunlap, Tennessee. The pressure is controlled by a blower motor, seen here, and the pressure is delivered to booths 1, 2, or 3, and flow to these booths is controlled by solenoids D1 and D2, which can be activated individually so that you can shut off the pressure to either booth 2 or booth 3. For our experiments, we ran them with the damper number 2 closed. So the system basically is set up like this with a block diagram. The function m of t is the manipulated variable function, which is what we control, and is a function of time, and it represents how much percent of the motor power input that is delivered to the system. The output that we get, this function c of t, the controlled variable that comes from the manipulated variable of the motor power, is a measure of pressure in centimeters of water that the booths are undergoing. More system information that we have. We input the controls that we have over the experiment include the experiment time, which has a maximum length of 45 seconds for the pressure booth. Which dampers are controlled so that we can say whether or not both damper 1 and 2 are open or damper 1 and 2 are closed. The input power from the motor of 0 to 100%. And we can also control whether or not this system has a step up response or a step down response. And we only ran that with the step response experiment, not for the steady state operating curve experiment. The pressure levels in the booth this block diagram represents how the information is gathered. We input the data into the web page, which sends information to a LabVIEW program. This LabVIEW program sends output to the equipment, which allows the experiment to run, and some of that input from the experiment is sent back to the LabVIEW program for continuing system information and run. All of this information is output to an Excel spreadsheet. The actual output is either a .text file or a .xls file, so that you can use just the text for other purposes if you so desire. The objectives for these experiments are to create a steady-state operating curve that relates the input power to the output in pressure of centimeters per water for the pressure booth system. And we are also supposed to observe a step response operation of the system. And that way we can determine the steady-state operating gain, the response time of the system, and the dead time, if any, of the system. For this, we are running the experiment with the second damper closed, and we are trying to obtain an output of 29 to 44 centimeters of water of pressure for our experimental range. We also aim to get 3 step up results and 3 step down results for the different sections of pressure ranges that the team was set out to gather. Here are the results from our steady state operating curve. You can see that this is just initially the motor was sent up to 70% of power, and then we ran the experiment for a total of 30 seconds to allow the system to reach the steady state. For this experiment, which was run at 76% motor input, we had an average output of a pressure of 35 centimeters of water with an uncertainty of plus or minus 2 centimeters of water. The uncertainty was obtained using the Excel function standard deviation for all of the data that we collected for the pressure output. The output is measured in centimeters of water, and the input, like I said, is measured in percent power to the motor, and these are both functions of time. For all of the data that we obtained for our steady state operating curve range, we were able to construct this steady state operating curve. We were able to determine that the pressure was a function of 1.1 centimeters of water per percent. So, and you can see that here by the fact that the output pressure is measured in centimeters of water on the y-axis, and the x-axis displays the motor input in percent of power. So therefore, the slope of the line, which was what determines the pressure, is 1.1 centimeters of water per percent. Here are results for a step-down experiment that was run at 100% initially, and then dropped down 29% to reach our desired output range. As you can see, this graph does not start at 0 seconds, and it did not reach the full 45 seconds because we only desired to zoom in and show you the pertinent information for the step response analysis. You can see here the difference in the yellow lines is the change in the motor input percent power, which was 29%. The change of our output, which was measured in centimeters of water, was 16 centimeters of water. That is an average value. The average value change was determined by taking the average of the steady state operation leading up to the step response and the steady state operation leading after the step response, which is how we were able to determine the change of pressure. We were then able to determine the steady state gain, which, as mentioned in the slide previous, that the steady state operating curve and the steady state gain is the slope of the line and the slope of change between the output over the input. And so we were able to determine for this step-down result that the steady state gain was 0.5 centimeters of water per percent. And once again, as with previously, the time is both of these are functions of time on the x-axis. You see the output on the right axis in centimeters of water, and you see the input in motor percent on the left axis. You can also see from this graph that we had a dead time, which is the time between the system's initial, the time between the system's told to jump and the time that we start to see an actual shift in response of 0.1 seconds. And then we were able to see the system's response time, which is the time between when the system is told to initiate the step response and the time that there's actual the time that there's a 63.2% rise in the delta C, which was determined to be 0.2 seconds for this experiment. Here is an example of the step-up response. We ran this experiment at an initial motor per input percent of 37%, and then we proceeded to step it up another 37% for this experiment to obtain our desired pressure output. Once again, we were able to determine using the average function on Excel that the delta C was 31 centimeters of water. The delta M, which we controlled, was 37% of the motor input, and this gave us a steady state gain of 0.8 centimeters of water per percent for this step-up function. We were able to determine that, much like the step-down experiment, that our dead time for this run was 0.1 seconds, and the response time for the system to reach 62.3% of the difference of water pressure was 0.2 seconds. Here are the average results for all of the experiments that we ran for our desired operating output ranges. For each of these represents the steady state gain for an experiment for the average of the for each region. The lower region, which were the experiments were run by David Harris, the middle region, which were the experiments were run by myself, and the high region, which were run by our other partner, Elise Garrison. As you can see, for the steady state gain for the step down results, we had about 0.6 as a statistical average, where the steady state gain for the higher region going down gave a statistically different average that was closer to 0.8. And you can also see that we had a steady state gain for the step up functions that were all fairly in the range, fairly statistically insignificant in the range of 0.8 centimeters of water per percent. And then for the step response, the results for the dead time, you can see that for the middle and the upper region of our data output desired values, we had a dead time of 0.1 seconds. These output were very similar, and you can see that our lower region had a very statistically different value for the dead time of the system, with large values of uncertainty as well. And these values of uncertainty were obtained using the student's T method of uncertainty because we did not have the minimum number of data points required to perform a standard deviation on them. And here, lastly, we see the step results for the time constant, which is the response time of the system to reach 62.3% of the desired output. You can see that for the higher and the middle region, for the step down function, we had about 0.3 seconds as our average response time, and we have a statistically different value for the lower region, which also had a large uncertainty for the response time. And once again, for the step up function, the middle and the high regions had roughly the same values in the 0.2 to 0.3 seconds range, and the lower region had a value of 0.4 seconds. In conclusion, we were able to determine that for the steady state operating gain, we had an average of 0.6 centimeters of water per percent for the step down, and 0.8 centimeters of water per percent for the step up step response functions. The dead time averaged 0.1 seconds for the step up and the step down step result functions. However, the lower region has a very great statistical difference from the middle and the upper region. And for the time constant, we had an average of 0.3 seconds for the step up and the step down functions, and once again, the lower region has a great statistical difference for our experiments. That's all I have. I'd like now to entertain a question as to why you may think that our lower region had greater statistical differences.
One clap for David.
Thank you.